Can the online students hear me? Can you hear me? Can someone type in the chat? Thank you. All right, I apologize for the delay. The CSIT building, there is some construction going on where my office is, and I could not figure out how to get out on time. I was running around. Okay, so I just want to set the context. This course, like I said in the first lecture, will give you a holistic view of a computer system with a focus on hardware-software interaction. And this is a limited view once again. I promise I draw the network after the teaching break. But the first 6 weeks, we are really going to set a solid foundation on these 3 key components. Once again, processor has direct access to main memory, all the data in main memory. It can use load store instructions to access anything, any byte. And then through the operating system, it needs to go to the IO devices, and the most important IO device in the first 6 weeks for us is disk or solid state drive or storage, which is far away from the processor. That's why we don't give it direct access to storage to the processor. It has to go through the operating system. We have to do a few special things. And also for isolation and protection, as we will see. Okay, so today and next week, we will try to strengthen your foundation on this piece here, the processor. You already spent a lot of time writing assembly, understanding how assembly language instructions are translated down to ARM, down to the machine code, how the bit patterns look like. And we will revisit some of that today and next week. But we are shifting away from the embedded domain in this course, and we are going to talk about x86, which many of you, most of you, use every day. It is the state of the art for servers, laptops, desktops, and Intel and AMD both manufacture different processors, different microarchitectures, different implementations of the same x86 ISA. Now, if anyone ever wants to ask question, why assembly again? Because we need hardware support, we need architectural support for concurrency, for networking, for other things. And we need to revisit these things in the context of the server domain so we can understand what kind of support is available for writing concurrent programs. And we need to understand the overheads. When we will write applications that will make use of the services that the operating system provides, we need to have an understanding of assembly so we can reason about certain types of overheads and make better choices. And we will see that. Function calls is an example. If we know how procedures work, if we know how stack frames are set up, we can reason about such things as iteration versus recursion. But we will see a lot more trade-offs. It's an evolutionary design over many, many years. The one thing, this is a very complex machine. This is a very power-hungry machine. That's one reason why Apple recently shifted to ARM for its laptop processors. One reason is backward compatibility. If you want a faithful user base, you don't want to break their software. People don't like to write software every 10 years, every 5 years. So x86 is backwards compatible down to 8086. You can run a program written 30 years ago on a modern x86 processor with a few changes, of course. It's a complex instruction set architecture. What is ARM? Is ARM a CISC ISA? No, it's a reduced instruction set architecture. A CISC ISA, or a complex instruction set computer, has more complex instructions. One example is in a reduced instruction set computer in ARM, you cannot have, as part of your arithmetic instructions, two operands where one is a register and where one is a memory location. You have explicit load and store instructions to bring information from memory into registers and then do the add or operations. x86 is more complex. As part of your arithmetic instructions, as part of many instructions, you can have very complex addressing modes. How you specify the operands in an instruction is called the addressing mode. We will see examples of that. And Intel, the conventional wisdom was that because RISC processors RISC ISAs lead to simple code generation, they're also faster. But for many years, Intel defied that, and they built very high performance processors that used the CISC x86 ISA. All right. So here are some definitions. So the first 8086 was a 16-bit Intel processor, basis for the IBM PC. It had a, okay, I really want to set up my, give me a minute. Address space. What is an address space? It's the amount of memory a processor can address. So if I have a 16-bit processor, all my registers are 16-bit, meaning any pointer that I have or any address that I have can only be 16 bits. And my address bus that connects my CPU, my processor to memory is also 16 bits. How big is my address space? Calculators, anything, use. 16 bits processor, how big is the address space?
The 64.
2 to the power 16, 64 kilobyte. Okay, this will get better over time. This takes a while. At the start of every semester, you have very bad handwriting, and then it gets better. So 64 kilobyte. But they did some neat tricks inside at the hardware level in the microarchitecture to get 1 megabyte. 1 megabyte today is a joke. But in 1978, people thought that 1 megabyte, wow, when will you ever need more than 1 megabyte? They were not foreseeing that people will be running Spotify, Word, email, Chrome with 500 tabs open, and Zoom, and Wacom tablet, and all that. So today, if you go down the evolution, 8086, 386, Pentium 4E, Core 2, Core i7, Core i9. One of the big push for changes in the ISA has been the need for larger address spaces. Our society produces more data, we need bigger memories, and we need bigger address spaces. That's why you hear 8-bit microcontroller, 16-bit 8086, 32-bit operating system, 64-bit operating system. Which operating system are you running? Which machine you have? This is what it means. 64 bits. With 32-bit, you can address 4 gigabyte maximum. And that was considered a lot in the early 2000s. 4 gigabyte, who needs more? And then AMD in 2003-04 introduced the 64-bit extension to the x86 ISA. And then Intel followed with different acronym, but similar.
Something I might have to know, but this is something I probably should have known already, but is memory space, address space and RAM the same thing?
Yes and no, and we will see. Okay, so the address space that I'm talking now is the physical address space. Okay, this is what the processor through its bus can access with, right? There is something else. It's called the virtual address space. But yes, this is the amount of RAM that you can, at this point, this is the amount of memory, this is the amount of RAM that you can access, that a processor can access. It cannot access more than, because you don't have enough wires, you don't have enough bits in your address bus to access more information. 2 to the power 16 tops. You cannot go above that. All right. So around 2004, 64-bit, you can access, I don't even know, exabytes. All right. Today, we think we will never need more. 64-bit is the maximum that we will ever need. Who knows? Okay. And they don't even use the entire 64-bit address space. The way they build the processor, they limit it to 48 bits because they are so overconfident that you will never need more than 256 terabyte. So any 64-bit processor today can access, that's a lot of memory. Around 2006, the first multi-core processor, 2004, hyperthreading. This is where the frequency scaling stagnated because of the power issues. Because as we shrink transistors, we cannot keep the power density constant. So Intel, AMD, they moved to multi-cores hyperthreading. If you cannot give the software people higher frequencies, you have to give them something. So they gave them multi-core processors where each core is a separate processor, and now the software moved to writing parallel software. And that's why concurrency is also important in this course. Another thing that happened over all these years is wider data types, 16 bits, 32 bits, 64 bits, SSE extensions, AVX, these are all extensions. So you can bring a lot more data from memory, 256-bit at a time, 256 bits, and do some arithmetic operations on the data. And this push is coming from neural networks, machine learning, where you have a lot of matrix operations. All you do is matrix multiply. And so these companies decided, we should provide some support for those things. So here you can see in the third column, the number of transistors over time. We are right now around about 6 billion transistors in a single processor. And we started with 0.3 million. So this is a lot of improvement. Okay. So when you implement an ISA, this is how your processor looks like. And we call this the microarchitecture. This is the implementation of the ISA. So here is some definitions. Architecture or instruction set architecture is only the part that of the processor design that the programmer or the assembly writer needs to know. And what are those things that the assembly writer needs to know? The type of instructions, instruction formats, addressing modes, registers, and then implementation. So ISA is like a cheat sheet. On the left, it has no physical value. And then you implement that on the right, which my students do in the microarchitecture course, and you get the actual processor. So microarchitecture has changed dramatically because ISA changes are more difficult because software breaks down. Software has to be rewritten if you change the instruction set. But with more transistors, we did floating point arithmetic, support for floating point arithmetic, wider data types. We will see support for concurrency and conditional execution. And most importantly, larger address spaces. We needed larger address spaces, larger memories. We were not happy with 1 megabyte, 4 gigabyte at any point in the last 4 decades, and this will continue to evolve. We don't know where we will end up with all the information that we are producing. So Intel and AMD are the two manufacturers of the x86 ISA, and all right, this is a slide that you can read offline. So let's start talking about x86 assembly, all right? We will do it quickly because we have a foundation in ARM assembly. The programmer visible state is the program counter, which is called instruction pointer in x86 64. So the 32-bit version of x86 ISA is called IA32, and the 64-bit version that we will study here is called x86-64. Once you know x86-64, you can go and learn any other variant. So register file, condition codes, program counter, and memory. These are the things that are visible to the programmer. Everything else Intel does inside that chip with you don't need 6 billion transistors for a register file and condition codes and program counter. They do a lot more inside to give us high performance, but we only need to know this, at least to write good programs. So what is an example? What are some of the condition codes? Do you remember?
Overflow.
Yeah, and? Zero flag. Negative. No, there's no, well. Overflow, carry flag. Those are condition codes. Whenever an instruction executes, most instructions, they change the condition flags, so programmers can reason about, overflow depending on what they are doing in their applications. So you will learn the flow, compilation flow in the labs, but I just want to do it here quickly. We will solely use C programming language in this course, and you will be using the new CC, the new compiler, which is or GCC, which is the default compiler on Linux all the time. So what we do is, right now we have make files and everything, where we are doing all of this for you. So if you have two C files, p1.c and p.c, p2.c, and you want to create an executable binary, you tell GCC to take these two files and output -o, an executable file that you can run. And the name of the file is P. What GCC, which is a compiler, which is the default compiler on Linux, what it does, first of all, it generates assembly. And you can generate assembly as well if you don't want to generate the executable file by using the -s when you run GCC. The assembler, or AS, then takes the assembly code and turns it into what? What does an assembler do? Machine code or object code. The problem is you have object code from two different files.
Does object code have anything to do with object-oriented programming?
No. It has nothing to do with the object. So object code is just a sequence of bytes. If you open a file, .o file, it will not make sense to you, but it will make sense to a hacker who is very skilled in reverse engineering object codes and figuring out what this code is doing. So object code obfuscates, hides whatever instructions in assembly or high-level language that you write. Okay, the problem at this point is we cannot do anything with these object .o files because they are not linked. We have p1.c and p2.c. And p1.c might be defining a function that p2.c is using, or p2.c might have a function that p1.c is using. This is how you write structured programs. Or you might be using an external library. What library have you used in the first lab? The standard IO library, the standard C library. The standard C library provides a lot of utilities, so you don't have to rewrite things that you want every day from scratch. The linker takes all your object code, object files. It takes all the libraries that you want to use, and it produces a final executable. Okay, so under the hood, when you type this, if you look at the make file that we are providing you, when you type this, you can type it in the terminal as well. I would really like you, and I will do demos here, I would really like you to become comfortable with programming in the shell environment in this course, and we will talk about that. You can do it in VS Code, or you can do it in a separate terminal, but this course is Linux heavy, and you will need to become comfortable with typing these commands in the shell. And Okay, just an overview what GCC does under the hood. And we will spend a lecture or two on linking. Linking is really important. So one thing here, the capital O flag -O, you could have -O1, you could have -O2. This is the optimization level. This tells the compiler what optimization level to use. Optimization, compiler can do different optimizations. When you write assembly by hand, you really have to work really hard to write very optimized assembly. What do I mean by optimized? Can someone take a guess? Right. The number of instructions that if you write assembly programs by hand, most likely you're not going to make the best use of the available instructions. And you may end up using 2 or more instructions for something that you only need, that you could do potentially with 1 instruction. There are a number of ways where programmers, the way they write assembly, they end up using more instructions than necessary. Compiler is an automated software tool. It can do a lot of analysis to really shrink the code size, the number of instructions in the program. The problem is sometimes you really need to understand what your assembly code is doing. The way the compiler transforms the code when you do very high, when you go to very high levels of optimizations, you cannot even tell what this is. This the high-level code that you wrote. So -OG, -O1, if you write a C program and then use -O1 or -OG, your assembly code will still mimic what you wrote in your C application. You can tell here's a for loop, here is a while statement, here is an if statement. But if you use -O3 and higher levels of optimizations, there is very little resemblance left. And sometimes you want to tell the compiler not to do certain optimizations because it could lead to security vulnerabilities, or there may be other reasons you don't want the compiler to do optimizations. So that's why there is a -O flag that tells the compiler what level of optimizations to do. -O1 and -OG do the same thing, but when you go to -O3, you see the code is really transformed. And try it. Write a simple C program in the terminal, fire up a shell, type the command -O3, and look at the assembly code. I'll tell you how you can do that in a minute. Now, in week 3 lab, we will do a little exercise where we will give you some assembly code, and that's the only time in this course you will write assembly. And we will tell you to hand optimize it and try to beat the compiler. Okay. If you're really interested, you don't want to generate the final executable yet, you could type the flag -S. Imagining, I'm assuming you have a program, some .c, you type -S, you will get the assembly. And this is how the x86 assembly will look like. Right now, it doesn't make much sense to you probably, but we will look at all these instructions, what they do. This is the x86 64-bit state-of-the-art server. Server machines are running this at the very bottom. So you could produce a assembly file, some characteristics of assembly. You have data values, data types, which could be 1, 2, 4, or 8 bytes. and you don't have any aggregate types such as arrays or structures. These are things you know already, I think. Okay, I already said that in x86, arithmetic operations can have both a register and a memory location, which is not the case in ARM, and we will continue to revisit the differences with ARM. Okay. All right, so if you don't want to produce the executable and you don't want to produce the assembly file, but you just want to produce the object code, you can use the -c flag. So GCC -c will produce the object code. So here, sum.c, when I produce the object code, it looks like this, 14 bytes, starting at some address. And we cannot really tell. Well, we can tell, but we have to work really hard to tell what these bytes really are. At this point, we are very far from the high-level language and assembly. So the linker will then resolve the references, like I was talking about. You know, if you have a call to printf, shared libraries, which we'll cover later. And then finally, you can get the executable with the -o flag. So -s will give you assembly, -c will give you object code, and -o will give you the actual executable. If you want to experiment with running the linker and assembler in isolation, it's a little bit tricky. It's not very simple because you have to include some other libraries that hook up with the operating system, that set up the runtime environment. If you're really interested, you can do the man page, the manual page, man LD, man AS, read a little bit how to run the linker and assembler in isolation, and try to do these 4 steps separately on your own. But it's a little bit more tricky. Okay. So this is an example of how the machine instructions look like and how they are translated to assembly. Okay, we have not systematically done assembly yet, but let's try to make sense of what's happening here. So what is this doing? So destination must be a pointer, which is not shown here. And what we are doing is, so what is this called? Star dest. What do we call this? Who said dereferencing? All right, good. It's called dereferencing. Okay. If I have a pointer with some address, what is P here? So look, labs are very comprehensive with respect to C. So we won't be doing C programming. Otherwise, you know, we're doing the same thing, labs lectures. So but let me do a little bit. What does it mean? What does P really is? An address, right? Can I say that it's a reference to a location in memory? Right? It's a reference. I have a hook to memory, so some location in memory, and I can I can use it. I have a channel. I have a something I can access a memory location with. It's an address, it's a reference, okay? But this is not very useful. I have the address, what do I do with it? Okay, it's an address, yes. What do we use memory for? Is address stored somewhere in memory? No, address has no physical storage. We put the address on the bus using high and low voltages, and memory produces something at that address, right? So what I have is a pointer, a reference to a location in memory. In order to get what is stored at that location, I need to do what? Dereference. I need to dereference something. Okay, we will be doing these things. We will look at assembly. This slide probably is slightly misplaced. Okay, so the assembly instruction, when the compiler transforms this C language statement to x86 assembly, what it is doing, this is the source. This is, so the pointer is stored in RBX. RBX is a register. What was the naming convention for the ARM registers? R0, R1, R2. You can call them anything you want. So Intel calls its registers RAX, RBX, RCX, RDX. We will look at it in a little bit. And the parentheses mean treat the contents of RBX as a memory address. There was something similar in ARM, right? In the load store instructions, there was something similar. So when you say parentheses, RBX is a register, what we are saying is treat the contents of RBX as an address and go to that address. And this instruction here, as you can tell, even though we haven't talked about any instructions yet, is what class of instruction is this? Does this look like? Yeah, move, but is there a class I can generalize? It's a data movement instruction. We have arithmetic and logic instructions. We have instructions for performing arithmetic operations. This instruction is a data movement instruction. It's a class of instructions that move information between memory and registers. Okay. And Q here means something we will soon see. The specifier Q means 64 bits. So we are telling the assembler that we are trying to move 64 bits of information from the register RAX to a memory location whose address is in RBX. Okay, so we will cover assembly in detail. This is just a warm-up. And then when everything is done, assembler does its work, the linking is done, you find this 488903 hexa in your final executable. It's a 3-byte instruction. Okay. There is a useful tool, object dump. You can disassemble object code and executables with this tool. So what it's doing here, it's taking the executable sum, and we are specifying the flag -d, and it's giving us the assembly. So from executable to assembly, we can do that with the disassembler, and the tool on Linux is object dump or obj dump. Okay, what are the two ways of producing assembly code that we have so far studied? One is what? Number one, we write C code and we do what? GCC minus capital S, we get assembly, right? The other way, produce the executable or object code and disassemble, right? Now I want you to focus and tell me, the one above is disassembly of an object code that I first created the executable and then disassembled. The second one is with GCC minus capital S. Tell me all the differences that you notice. Okay, one thing we notice is that there is the address space where the disassembled executable is kind of different from what we have at the bottom. What is the other difference? By the way, I forgot to mention, okay, before that, keep thinking about the differences. What is strange here, if I were to show you ARM assembly instructions, each of these 1, 2, 3, 4, 5, 6, these are 6 x86 instructions, okay? If I were to show you 6 ARM instructions, what is the difference that you notice here?
It'll be the same.
ARM instructions are all the same size or length. It's a fixed width ISA. That's the philosophy of RISC, reduced instruction set computer. That's the philosophy of ARM. Build simple machines, simple hardware that consume less power, less energy. That's why it's in the mobile market. Okay. Intel does things differently. You have instructions as small as, so each one of these, this is in hexadecimal. What is the smallest instruction size of instruction you see? 8 what? 1 byte. The first instruction, 53. 5 is a hexadecimal digit. A hexadecimal digit is how many bits?
4.
Yeah. A hexadecimal digit is 4 bits, right? 0 to 15. Some instructions are 3 bytes and some instructions are 5 bytes, all right? It's a variable weight ISA. So we will look at x86 this week, and next week we will see instructions that are variable size. This makes hardware a little bit complex because decoding instructions that are not placed next to each other at the same distance apart is a little bit more complicated than if everything is nicely 32 bits apart, you know exactly where the next instruction is. Here, actually, you know where the next instruction is. They do some tricks. How they encode the opcodes. You can tell an experienced, x86 assembly person can tell that this sequence can only begin when there is a new instruction. But we are not going to go in that depth. This is when you do software security, network security, when you start hacking other people's machines and all that. Okay, so there are two differences. No, there's one subtle difference that is really important. So this is an eye test. Figure out what is it. So instructions, sizes, okay. This is the difference between ARM and x86. The addresses where the instructions are placed in the address space are different. This is, I'll explain why is that. Why is the linker doing that? But there's one other difference. Huh? Oh, which line? Huh? Oh yeah, fine. Okay, that's fine. The address space. So you're actually allowed to go up there. Okay, this starts at 0, and that starts at 00004000595. Okay, I get that. That's one difference. What is the other difference?
Address for function.
Exactly. When I'm doing the -s, when I'm doing the -s, the assembler has no information where the call is, right? This call here, the plus function, assembler has no information. It is in isolation, assembling one file at a time. It is the job of the linker to figure out where all the function calls are, merge all those object codes into one large executable, and then fix all these references to function calls. So linker knows, because it has done all the merging, it has fixed all the startup code, it has copied all the libraries that the program wants to use, and it has created this one large executable where all the code the application needs is nicely placed in a new address space. It can now fix the address of the call because it knows where the call is, where the code for that function is placed. Okay. So linker has shifted the location of the code to a different range of addresses. This is important because when you start putting library code, when you start bringing code from other files, and you want to create one large executable, of course, you need a different address space. The address you use in this large executable will be different from the original. What? No, it's not. Okay. Partly, yes. It is. So let me come to that. So required for merging with other code files. So we will spend a lot of time on virtual memory, but all I want to say is whatever the linker generates, when you compile applications, the addresses you see are called virtual addresses, because what you are creating is a binary executable. This binary executable, this binary file or executable file is not running yet, right? We are just compiling it and storing it somewhere. You run things when you double click on an icon, or in a shell, in a terminal, you type /, the name of the binary. So at this point, all the addresses are called virtual addresses. So all these addresses here are in a virtual address space. This is a made up 64-bit address space that the linker is using. The linker is assuming that all this space will be available to this executable when it runs. It cannot make any other assumption because it has no clue at this point what will actually run alongside with this executable. At some point in the future, when the executable actually runs, the operating system does the virtual to physical address translation. The physical device, the physical hardware, the physical memory chips are not visible to the linker. The linker doesn't know where this binary will run. Will it run on Ben's laptop, or will it run on Adam's mobile phone, which will have 1 GB memory, physical memory? It has no clue where it will run. So it just assumes a flat 64-bit address space, and we call it the virtual address space. And when the binary actually runs, the operating system intercepts all the virtual addresses and actually transforms them to physical addresses. So we will study that at some point in a lot of detail. But you will encounter this terminology in the labs, virtual addresses. That's why it's important that at least I mention it here. So each compiled binary has the illusion that it has 64-bit address space, 256 terabytes, all for itself. It has this illusion that is fully isolated. It's the only thing running on the system. It's the job of the operating system to intercept all the addresses and use whatever is physically available. All right, so the linker, because it merges all the object code and creates one large executable, it has a knowledge where the code for a function call is. Assembler has no such knowledge. So this is something you can try. If you write this program and you produce the object code only, and you look at the size of the object code, I did that last night, and it was less than 2,000 bytes. And if you look at the size of the executable after running the linker, the size is 16 kilobyte. Now, why is that? Why is the executable so bigger than the object code? And here, I'm not even using, I just have a main function with a function call, and then some sloppy pointer arithmetic and a plus function. So object code is, for this file, I'm not even including any libraries. I'm not even using C library. I'm not even using printf, right? All right, so our applications need a lot more than this code to run. And we tell ourselves a lie all the time that main is the first function that is run when an application starts. It's not. There's a lot of things that needs to happen before that. When you double click an icon or you type an executable's name in a shell environment, the operating system needs to do a lot of things that your application runs in a secure environment. So it's fully isolated, that it has proper access to certain environment variables that it needs, and a lot of other things. And all of that code, all of that work is done by the linker when it produces the executable. So if you look at the executable, the size is much bigger than. Okay, so try some of these things. Open up a terminal, spend 5-10 minutes, become comfortable with typing GCC -S -O. Look at the sizes of different files. How many of you have used shell before? How many of you have used shell in VS Code? So I would really want you to spend no more than 5 to 10 minutes opening the terminal and becoming comfortable with writing these commands. And how can we try to figure out how you can check the sizes of files, how you can maneuver, the file system, how you can list the files, a lot of that. If you want to become a systems programmer, you need all these skills, right? You cannot become a systems programmer in a graphical user interface using, Visual Studio or whatever that is. Oh, we will support it, but I'm just saying. So, and soon in lab 2, you will encounter, we want to teach you how to systematically debug system software. Typing run and debug from VS Code is good as long as you're writing business intelligence and all that software. But we want to teach you how to disassemble C applications, object code, how to debug more deeply. And you will learn a few tricks in lab 2, 3, 4, 5. Each lab will introduce. So if you encounter GDB, this is the new debugger. Just like GCC, GCC is the compiler, GDB is the debugger on Linux. And all of these tools, all of this is on CSID machines, on our Linux machines. So you will need to do all these things there or set up your own Linux environment. So historically, up until x86 IA32, 32-bit ISA, there were only 8 registers in x86. But when they moved to x86 64 bits around 2007, they introduced 8 additional registers. So the names here, there's a lot of history here. You see, we started in 1978, and this ISA is still backwards compatible. There's a lot of things you will probably need to search yourself. If I start doing it, why did they come up with AX, BX, CX, DX? We just have to take some things as they are. So these are the registers in 64-bit. You can access 32 bits. There are instructions to access 32 bits or 64 bits. So 64-bit register is called RAX, RBX, RCX, RDX, RSI, RDI, RSP, and RBP. Can someone guess what would RSP be? Stack point. Good. BP? BP is something I know that you don't use in COM 2300, and I've been telling them to teach them to you. Oh, break.
Yeah.
No, base pointer. It's a base pointer. We will look at base pointer. Base pointer also helps with procedure calls.
And what do the R and A stand for respectively?
R is when they move to 64-bit, they register BP, register AX.
base pointer is the same thing as a frame pointer?
Yes. So base pointer is when you save the stack pointer of the previous function call, because base pointer is the point at which function call was made. You preserve your stack pointer because it makes it easy to access arguments and other things. And stack pointer changes all the time as you push and pop things. So it changes all the time, you lose it. So if you want to fix your base pointer to when the procedure was called, you save your stack pointer at that point in your base pointer, and then you can use it to access arguments or other things below and above, because the base pointer is fixed anyway. So we can still access 16-bit registers are called AX, CX, DX, BX. 32-bit registers are called EAX, extended. E is for extended. EX, ECX, EDX. It's a backward compatible ISA. And there are historical names for different registers. There were conventions that this register should only be used for this particular thing, but they are general purpose registers, except for stack pointer and base pointer. General purpose registers are those which any instruction, most instructions can use. So if we look at the C data types, character, short, int, long, pointer, float, double. The x86 assembly uses many instructions are, if we add BWLQ, they operate on that data type. So a character is 1 byte in C, and in Intel assembly, we refer to it as B. It's 1 byte. Short is Intel's data type word, which is 2 bytes. So word is 16-bit in x86 assembly. Integer, 32 bits, we say L. Quad word is 64-bit. What does this line means? So C declaration, what data type is this? Huh? String. What if I say in terms of how big they are, is there any difference between int star and char star? They are pointers, right? And what is a pointer? What does a pointer contain? A memory address. And on a 64-bit machine, how big is the memory address? 64 bits, right? So quad word is 4 multiplied by word in Intel assembly. Word is 16 bits. This is the convention. So 64 bits is quad word, and the assembly code suffix is Q. And a lot of instructions need the suffix to know what data type are they operating on? You might have noticed there was a lot of Q in the assembly examples that I showed. So here you see, right, call queue, return queue, move queue. Queue here is telling the assembler that you are operating on quad words, 64 bits. This is why this is a use of this table. And then floating point, we'll discuss them later. They can go up to 80 bytes. So the important thing is that an integer is 32 bits and a long is 64 bits. An address is always 64 bits. So when you write programs in the labs, you have to use the correct data type. Because you will be doing low-level bit manipulations, low-level operations, you have to figure out if a specific data type that you're using will overflow, and you have to know that how many bits are you using. If you're using an int, it's 32 bits. If you're using a long, it's 64 bits. And if you're using a pointer, it's also 64 bits. So we will use this suffix often, B, W, L, Q, S. We will not use S. We will not deal with floating points. So when we use the suffix, we will be talking about a byte or a word, but mostly we will use Q. What? Oh, that's because of floating point. So we'll talk about it later, but when you use floating point types, the processor has more information and the assembler has more information to use the correct type, S or L, because there's a separate coprocessor and all that. There's a lot of detail. So
both of them are quad words, and in long they are 8 bytes.
long?
Long and char stuff.
So long is a data type. Long is an integer data type that is 64 bits. Okay.
I mean, in terms of the size, they have the same size.
A pointer has to be 64 bits on a 64-bit machine, because you have an address space that is 64 bits. So a pointer is always, on a 64-bit machine, it's 64 bits. And on a 32-bit machine, any pointer, regardless if it points to a character or integer, it's 64 bits. So when you use double precision, there is more precision in your floating point data type, more digits after the point, and those opcodes are very different. So the assembler knows that if we're talking about a floating point data type or a integer data type, because the opcodes are different. So the convention we will use for move instructions. So let's cover the move instructions, the data movement instructions. The way we will write is move Q. Now this Q could be B, L, W, anything from the previous table, but here we will just look at all examples with Q. The first operand is the source operand, and the second operand is the destination operand. And when we use constants or immediates, it's called an immediate because it's encoded in the instruction. So it's immediately available to the processor. You don't have to bring it from memory. We will write constants as $, and the rest similar to C. In C, you can write 0x 400 or $, a number, but we'll prefix it with a $. Right. So there are different formats. I just want to have a quick note that the format that we will look at is AT&T format, ATT format. This is from Bell Labs back in the day. This is a default format on Linux. So you will only encounter AT&T format where source is first and destination is second. But if you go to Microsoft compiler, you might see a different format, Intel assembly, where everything is a bit different. So just be careful if you ever encounter Intel assembly. It will not look, there will be differences. Okay, so how does a move queue instruction works? We first have the source and then the destination. The source could be a constant, an immediate, a register, or memory location. And a destination, can a destination be constant? It doesn't make any physical sense to have a destination as a constant. So these are the combinations you have. Your source could be an immediate or a constant that is encoded in the instruction. The processor doesn't have to go and fetch it. It could be a register or memory, and your destination can only be a register or a memory location. So here's a starting example. You are moving a constant into a register. Quickly make up a C statement that is equivalent of this. Don't define it. Don't declare it. All right. So a C statement would be any variable name being assigned a constant. This is the assembly. So always remember, especially in the lab where you will do assembly, that source comes first, and then we have the destination. Parentheses, once again, whenever you have parentheses around a register specifier, it's telling the assembler to treat the register, to treat the operand as an address. And the address is stored in the register RAX. So whenever you see parentheses, it means go to memory. Where in memory? Read RAX and figure out which address.
What's the Q stand for the instruction?
That we are just telling the assembler that we are dealing with for 64-bit quantities. Sometimes it can figure it out itself, but sometimes it's a safe practice to write Q. In fact, you have to write it. You can write, you can have, so there are 4 variants of the move instruction: move Q, move B, move L, and move W. Just to tell the assembler that I want to move 8 bytes. I want to move 16 bytes. I want to move 64 bytes. So here, I'm using the full register RAX. So I'm moving 64 bytes. So it will treat the 0x4 as a 64-bit number. So what's an example? I think you should write in your notepad, what's the C statement for this instruction? Some of you has everyone done the first lab? So what are we doing here? Dereferencing a pointer, right? Suppose we have a memory address that is stored in RAX. We are saying, take that address, go to that memory location, and store -147 at that location. The star P, if you read the lab handout carefully, we explain everything, is dereferencing a pointer. Of a variable. It's an address of a variable. It's some address. So here we're not going to write the entire programs. We're just going to assume that P is a pointer. What is this doing? Moving one register value to another register. It's moving RAX to RDX. What would be a C statement that would assemble to this instruction? Yep. Bullseye. Two variables that are stored in two different registers. We are saying move one to the other. All right, what are we doing here? Great, star P equals temp. We are saying take this address, parentheses say, treat the register as address, take the variable that is stored in RAX and store it in memory. The processor has direct access to memory. It reads the instruction and puts the hex register value and does some circuit stuff to store. Okay, what is this? Right. So this time we are doing the opposite. We are saying, once again, this is the source and this is the destination. This must be a variable because this is a register. When we write C programs, we declare variables, we use variables, int x, int y. There is no such thing in the processor. The processor just has a register file. So assembler or compiler together, they pick, sorry, the compiler. Assembler does not do that. The compiler transforms the C code into assembly. The compiler picks some register and for each variable that we declare in our C program. And it uses very complex heuristics because we have very limited number of registers. But the applications you write, you probably create tens of variables. So this time we are bringing the contents of the memory location. What location? The address is in RAX. And we are bringing it and storing it in the variable that is represented by RDX. So what is missing here? Register memory, yes. Memory register, yes. Memory. Why? When you write applications, structured programming, others, have you ever noticed the need for, what do I call it when I do a memory to memory transfer? Copy. But copies are ubiquitous. Copies are everywhere. We copy something every day. We copy things from here to there. So why are there no memory to memory transfer instructions? What? Why? Yeah, but you know, 2 instructions, right? But we're talking about assembly. We're not talking about C level, right? Okay, memory to memory transfers. This is an important thing. They would require extra circuitry in the processor. And that circuitry could be very complex and could be very complicated. Okay. The memory chips are made by some other guys, you know, Micron, Samsung. The processor chips are made by Intel, AMD. So this interface that, all right, the processor guys, Intel, AMD say, look, we will have these instructions and your memory system has to be able to, you know, help us bring information and store information. When you start doing memory to memory transfers, you have to go talk to those people. Hey, we have this instruction that does a memory to memory transfer. You have to support it because you are the one making memories. So we don't want to bring something in the register file and then store it. That's 2 instructions. We want you to provide us support for this type of instruction. And this kind of communication doesn't happen. Historically, companies, vendors want to innovate separately. You know, we are the processor people. We will just focus on the processor. If you start in this direction, then you are tied to, then the memory guys will say, look, we are not going to support this anymore. And then you're like, you know, hey, don't do that, please don't do that. And there are a bunch of other reasons for, all right, so these kind of questions are important for you to think about, you know, how does technology impacts what you can and cannot have. So here is some explanation for you. So what is an addressing mode? An addressing mode is how do you treat an operand? We have already seen a couple of addressing modes. Constant, immediate, that's an addressing mode. The operand is immediately available. Register, memory, that's an addressing mode. So an addressing mode tells us that we can insert the parentheses and have a memory address. We can treat the operand as a memory address. When we don't have the parentheses, we can treat it as a register. Every ISA has a number of addressing modes that we need to know. And this is what they tell us. How should we treat an operand? We can't just randomly assume that parentheses means something. So whenever you see parentheses, this is, we already discussed pointer dereferencing in C. We use it like this. This is a register. And the semantics, the meaning of doing that is go to the memory location and treat the register R as an address. Register R means the value that is stored in R. Okay, and then we have seen examples of source, destination. Okay, the other addressing mode is displacement, where we add a displacement to the normal mode. So dr means d could be a constant and r is a register. So this example here means whatever is stored in RBP, add 8 and go to that memory location and bring that data into RDX. So it's the same as a normal mode, but you're adding a displacement. When is it useful? Someone else. Huh? Yeah, but even if you don't have the displacement mode, you're still reading in the normal mode. Why do you need displacement? Why do you need this displacement?
Is it to look for a bit shift?
No, no.
You can use that instruction. You have to add first and read.
Applications use arrays, structures a lot, and there, displacement is really useful. And let's see an example. So let's say I have and this is an integer array where each one is 4 bytes. So this array has a base address somewhere in memory. And now I want to go to, let's say the base address is stored in RAX. Whenever you create data structures in your programs, they have to be somewhere in memory. So if that's the case, then the array must have a base address where it starts in memory. We can store that base address in a register. And then if we want to go to the last element of this array, what displacement do I need? Right? So from the base address, if I add 12, I can access the last element of the array. So this will translate to the C statement something, right? So arrays, structs, they are placed somewhere in memory. They have a base address, and what programmers typically do is they access array elements by using index I or something, array 0, array 1, array 2, array 3. In a for loop, for instance, this programming practice is very common. And to support that, we have this addressing mode where we can specify the displacement on top of the base address that is stored in a register. So typically, we store the base address somewhere in a register, and then we use the displacement to access different elements of a structure or an array. Now we started late. I think we should finish, huh? Or should we continue?
I got a.
All right. I'm also, this is the end of my first week, 4 lectures, 7 labs. I really need to go home. Thank you, everyone. We will start with this example. Notice that you don't have to get scared. Assembly is a little bit scary. We won't be writing assembly in this course. We will reason about overheads. You have to understand the instructions, what they're doing, the mechanisms, and you have to reason about overheads when we write certain types of C statements, but we won't be writing assembly the way you did in 2300. So don't be scared of assembly here. Just try to understand examples and all that. All right, thank you. Yeah.
One more question. Because in ARM assembly, sometimes when we did a compilation and we looked at the about code, sometimes it stored variables on the stack.
You can store, yeah, you can store. It's the same execution environment. Everything is the same. So when you run a function, you store variables on the stack. You push and pop variables on the stack.
So do you typically use registers or just?
When you run out of stack space, you use registers. Sorry. When you run out of, sorry, I'm completely. When you run out of registers, you start using the stack. So let's say there's a lot of pressure on the register file and you don't have enough registers. And so let's say you have something in RAX and you don't want to throw it away. It's still live. The application still wants to use it. And you don't have enough registers. What do? You push RAX on the stack, you use RAX for something else, and then you bring back RAX. So remember those conventions, caller will preserve this, callee will preserve this.
Yeah.
You made it. Just
Well, that was really nice, but I had discussions with them. They let me.
well, that's great. Yeah. Next week we will, fire up. These are some of the things you already know.
Yeah.
What?
Good revision.
Yeah.
But I need to catch up on the lab.
Oh, okay. We need to talk because I want to talk to my 2219 students because we have time now or so hold on a second. Let me. I see you in the other. I also see you in microarchitecture.
Yeah, I'm doing both at the same time.
Really?
Yeah,
It is very different levels.
yeah.
I have a 10. This is the first time they've given me a 2000 CS course, and I have no clue.
No. Just with the special topics in computing, I didn't know whether it would continue to be offered, and it seemed like a real